Okay, so we have those two. Then, of course, we are left with three more terms, this, and that. Okay, now what does this one do? So this one will, of course, act on this and give me the atomic energy. Similarly, this one will act on this and give me, because these are eigenstates of these atomic Hamiltonians. So they will give me atomic energy times that wave function back. All right. Okay, so if I take this plus this, then product of these two will just give me, apart from this factor, which is always there, so I'll get two factors of the atomic energy. Okay. And then because these wave functions are not orthogonal, but they're normalized, each one of them is normalized. So that integration will give me 1, both the integrations. So I get that as the first term. So these two are sort of taken care of. Then I have R1 over R1 minus 1b. So when I take these two terms and I take this term, then of course the R2 integral is complete because it's just give me 1 because of the normalization of phi b, but this R1 integral will remain. So I'll get so there should be a 2 over here. Okay, so for simplicity, let me just call this constant something rather than writing it every time. So just let us call it a capital A. So then I have no, sorry, these are minor. Okay. That is a plus. Yeah, so I have a A here, and then I have from these two, I'll have but then, yeah. So similarly, when I take this term, the R1 integral will give me 1, but then the R2 integral will remain with mod phi b squared. So I'll get a similar term with okay, so I have these two. Then I have, of course, this one. Okay, I have to make some space here, so let me write this once again here. All right, so finally we are left with this. So I'll have the usual E, then I have okay, so that's just the first of these terms. So I'll have similar other terms when I consider the subsequent terms. So let us just look at one of these. Okay, so suppose I'm looking at this with the last thing here. So when I take the atomic Hamiltonians, so let's see, R1 minus RA. So this one, yeah. So so this atomic Hamiltonian will act on this one, or if you wish, because this is a sort of Hermitian Hamiltonian, so it will act on this side. So it will give me just the atomic energy. Similarly, this Hamiltonian can act on this state and give me the atomic energy. So the atomic energies will be obtained, but in this term, when we are looking at these two, the subsequent R1 and R2 integrals just give me 1. But here they won't give me 1 when I take this with the last term, because I have a phi A star R1 here, but I have a phi B R1 here. So I won't get the ones. I would rather get the sort of the exchange terms. So which, well, not really exchange terms, but 1 and 2 have R1 and R2 have interchange there. So it will eventually give me the overlap integrals when I do the integrals. Okay. So so let me write that. So I'm writing this with the Hamiltonian in between. Okay, so that is obtained from one of these. The other will give me exactly a similar term. So I could have just written a factor of 2 there. So basically the same integral over here. Okay, and then I'm looking at R1 minus RB term there. So what does it give? So when I take RB, so I cannot perform the R1 integral because I have 1 over R1 minus RB here. But I can do the R2 integral. And what do I get when I do the R2 integral? Phi B star over here, phi A over here. So it will give me the overlap integral. So I get the overlap integral L. And then I'm left with phi A star and phi B. And obviously, I'll get a similar term when I take this. So there, the R2 integral will remain. And then, of course, finally, the 1 over R12 term. Okay, so these are the kind of terms that I get when I take this with this and then this with that. Now, I think here I have to keep the other two terms because let me tell you what you'll get. So this will be a star here. So when you take this with that, you'll get terms apart from signs. You'll get terms exactly like this part. So this is one part. This is another part. So when you take this with this, you'll get terms that look exactly like this, apart from signs here and there. And when you take this with that, you'll get terms that look like that. Okay. So this is something you have to sort of work out. And after doing this, all of this, I'll tell you what you get. So first, let us identify what are the different kinds of terms that we are getting here. There's one type of things here, which is sort of straightforward. And I'm numbering them just for understanding. There's no sequence in here. Then there is certain kind of terms here, which I just termed as 4. And then I have this over here, which is another kind of term. Yes, is there a question? All right, and these are another kind of terms. These are another kind of terms. And finally, this is another kind of term. So you get 6 different types of terms. And when you work out these two matrix elements, I mean, matrix elements of H between these two and this, you'll get these 6 different types of terms. 1, 4, and 5 appearing when you take this and this, and the others appearing when you take this and that. Okay, so I'll leave that for you to work out. So eventually, I'll skip 1 or 2 steps and then I'll write what you get. Okay, let me write the final step because I'll ask you to fill in the intermediate steps as an exercise. So this is here. Okay, so this is the final form that you'll get. So you have to work out this thing. I'll give it as an exercise. So now let us get to our argument. So what are we trying to do here? So we'll write this as so 1 over 1 minus L squared is common in both the terms. So this part from here to here, this you should be able to recognize that when we did the discussion of exchange earlier, this appeared as, and what we called this was the Coulomb term. So this is like density interaction, classical density interaction. So here now this term appears, but in addition there are two more terms, which is like density of A state with the nucleus at RB, and here is the density of the B state with the nucleus at RA, because now we have two nuclei. So this whole thing we'll call C12, our new sort of Coulomb interaction term. So this includes electron-electron and electron nuclear Coulomb interactions. And then this is like the earlier exchange term, phi A star R1, phi A R2, phi B star R2, phi B R1 with 1 over R12. But in addition, we have similar terms involving the nuclear coordinates. Here, phi A star R1, phi B R1, and the other one. So this whole thing will be written as the exchange term. So basically, we call this whole thing as I12 with 1 minus L squared, right? Okay, so these are just definitions, C12 and I12, but this is how we write it. Now the question is, so this is, what is this? This is the energy of the triplet state. Sorry, it should be a plus sign. Yeah, there's a plus sign. So this is the energy of the triplet state, because you remember Psi1 was one of the triplet states. So one has to similarly calculate energy expectation value in the singlet state to see what is the singlet state triplet energy difference. Now, calculating this for the singlet state obviously is going to be even more complicated, because it has 2 terms in the spatial part, 2 terms in the spin part. But if you go through the exercise and you calculate this, what we'll get is this. Okay, so the sign of the sort of exchange contribution changes as it happened in the earlier case. So now what we look at is, so we want to see what is the energy difference between the 2 spin states. So if you work this out, what we get ultimately is I'm missing some sign somewhere. Yeah, this is a plus. So given this, we can write as before. And okay, so this is termed as G12. So if you write it this way, you should be able to figure out that, it should turn out that in one case, triplet has a lower energy, in other case. So we'll come to that. Okay, so so what do we want to argue from here? So let us see what happens when, let's say, the separation between the atoms is large. So what happens? Which quantities gets affected in this? So when the separation is large, what is the value of L? Yes, someone, what is the value of L when the 2 atoms are at large separation, whatever that large means?
So it should be 0.
It should be 0. So the only thing that remains is this minus. So J12 becomes minus I12 with a factor of 2. Now I want to exchange it. It is so the I12 part is positive. So this minus I12 is a negative quantity. So therefore, S1 and S2 would like to prefer to align in the same direction, which will lower their energy. So essentially, what we have is a ferromagnetic coupling. I mean, it's a coupling. So the value of J is such that spins tend to or like to align with each other. So that is what we call the ferromagnetic coupling. And then what happens is, as you decrease that distance, L starts increasing, and there comes a point when this term should dominate this, okay, because when L becomes large. So then at some point, at some separation below which the sign changes. J12 changes the sign. When it becomes negative, then no, when it becomes positive, it was negative. So when it becomes positive, it is energetically favorable for the spins to anti-align. So that is what we call an antiferromagnetic coupling, an antiferromagnetic exchange. So we have generated an effective spin model in which the coupling can be tuned sort of depending on the distance between these two atoms. Okay, so this is the point this is the part that was missing last time. The direct exchange between orthogonal orbitals that we discussed earlier always gives you a ferromagnetic coupling, but then there are more antiferromagnetic materials in which successive spins are sort of oriented opposite to each other. So now we have a rationale for that. We have one mechanism, we have arrived at one mechanism which can give us antiferromagnetic coupling between spins on two different atoms. So both these examples, both these sort of ways of looking at exchange are called direct exchange. So that was direct exchange between orthogonal orbital. This is direct exchange between non-orthogonal orbitals. Okay. So that much is fine. Just give me a second. Yeah, right. So this analysis, I think I mentioned it last time. This is essentially based on what is called the Heitler-London theory of the hydrogen molecule. And so basically, all right. So now, what have we achieved here? What we have achieved is that we have arrived at an effective Hamiltonian, spin Hamiltonian between electrons on two different atoms, which can be either ferromagnetic or antiferromagnetic, depending on this quantity L. So what actually happens in the hydrogen atom, if we confine ourselves to the hydrogen atom. Well, what happens is that irrespective of the separation, the ground state always remains a singlet. Because you know that, when you have two hydrogen atoms at equilibrium separation, their equilibrium bond length is, the value is not important, but nevertheless, 0.74, 0.75 angstrom. At this separation, the two electrons are in a singlet state. Now, according to this argument, as I increase the separation, L decreases, and there should be a point beyond which the triplet should start becoming the ground state. That doesn't happen. Okay. So what I'm now trying to tell you is that what are the sort of difficulties with this approach, or where it doesn't quite work, and is there another way of looking at things? So as I said, in the hydrogen atom molecule, it doesn't happen. It always remains a singlet. So at large separations, there is a problem. There is a problem that this argument would tell you that at some point there should be a triplet ground state, but that's not seen. So how to look at this? Now remember that, so this gets us really into the sort of complications of many electron physics. And in this course, of course, we cannot get into all the formal complications or how to deal with many electron physics. So I'll just try to give you now some snapshots of what the problems are, or whether each phenomena are, and would sort of try to impress upon you that magnetism is one of the aspects of a very rich physics of interacting many electron systems, and it is intimately coupled to many other important things, which could be, and something we'll look at very soon, that is metal insulator transition, but also charge ordering and various other things. So I'm just trying to give you some flavor of that without, of course, getting into the full formal theories of any of these. All right. So, so there is a problem at large separations because we don't get a triplet state. So what is happening? So let us try to look at things a little intuitively. What will happen? I'll now erase this. I hope it's okay. So when they're at a relatively large separation, now the term large is of course vague to some extent, but nevertheless, let's say larger than equilibrium separation. So what will happen is there'll be a bonding state and an anti-bonding state, and we know that electrons are in the bonding state. So, because we have got a singlet ground state. So anyway, so we have a bonding state which has large amplitude here in this region. So I have two electrons in here. So they feel each other more than they feel any of the nuclei. Okay. So then the electron-electron interaction becomes a dominant thing here. So in such situations, we have to go beyond. So what the terms that we had in what we wrote down when we calculated the expectation value of the Hamiltonian are the Coulomb terms, which is just a classical charge-charge interaction, and the exchange term, which arises because of antisymmetric nature of the wave functions. But there are effects of interacting electrons beyond the Coulomb and exchange, and those are called correlation effects. So in fact, whatever is beyond exchange is by definition the correlation effects. Okay, but the point is that there are effects that go beyond the exchange term, and those are called the correlation effects. And in order to get or sort of capture those correlation effects, now there's a bit of formal theory which I cannot discuss here, but one cannot confine oneself to just the sort of ground state Slater determinant wave function. One has to look at higher energy Slater determinant wave functions in order to capture those correlation effects. So those are called, I'll just give you the name. I mean, I'm not really expecting that you will really appreciate it from what I'm saying, but there's something called configuration interaction, which is a technique or a theory by which you can capture such electron correlation effects. So my point here is that just carry this much in mind, that at large separation, the electron-electron correlation effects become important, and which have to be captured somehow if you want to try to get the correct ground state. That's the sort of final statement. Okay, so that was point number one, correlation effects. The second point is even at small separation, okay? In this Heitler-London theory, what we always assumed is that one electron is in the orbital phi A, the other electron is in orbital phi B. So one electron is on this atom, the other electron is on that atom. Hello, can you hear me?
Yes, sir.
Somehow this connection got disconnected for a few seconds.
Yeah.
Let me get back to this. Okay, so where was I? So at small separations, so we never considered configurations in which both the electrons are on the same atom, both the electrons are on phi A or both the electrons are on phi B. We never considered such configurations. So those configurations can be termed ionic configurations because one of the hydrogens, let's say, becomes H minus. So in Heitler-London theory, you do not consider such ionic configurations, but at small separations, it is possible that at some time, both the electrons are on the same atom. Of course, it will cost energy because they will experience Coulomb repulsion because of each other more. But as we will soon discover, this has some other effects, other consequences. So then what I'm saying is now that we consider, let's say, ionic configurations and figure out whether these are important or not. So what would be ionic configuration? So we could have a situation when both the electrons are on phi A. So we could have a configuration that we call psi A, which is, so both electrons are on phi A. So we simply have, but then the spin part has to be antisymmetric. And similarly, I can have a phi B. And obviously, both are singlets, right? If you have two electrons on the same orbital, then it has to be a singlet configuration. So that is that. So the question is, why are these important? Are they important? So the Hamiltonian that I wrote, H effective, or let's say H equal to half epsilon singlet plus epsilon triplet minus G1 2 S1 dot S2. I can consider this to be a Hamiltonian. Think about this in the four-dimensional space of the three triplets and one singlet, right? This was a plus. So if I write this Hamiltonian in that basis of three triplet states and one singlet state, then I can view this as, I have to erase this part. So it's a diagonal thing with definite energies for singlet and triplet states. These are the three singlet states, three triplet states, and this is the singlet state, and of course this part is diagonal. Okay, now what we are saying is that there could be other singlet states in the ionic configuration which we did not consider earlier. So for the moment, let us forget the triplet part. We look at the singlet part and ask, is there a connection between these singlet states and the singlet state we considered here, the singlet in the neutral configuration and the singlets in the ionic configuration? Are they coupled? So what is meant by that coupling, or what is meant when if we ask, do they mix? So I have a certain Hamiltonian, and I can calculate, and I know that, I can calculate the expectation value of H in the psi4 state. But then if I have this matrix element, I'll write what psi5 is as not equal to 0, where psi5 is, let's say, what is the factor? How do I write this? Okay. So it's a linear combination of these two singlets, okay? So if this happens to be non-zero, then of course the electrons can make a transition from the psi4 state to the psi5 state. It's like the hopping matrix element in your tight binding model. Okay, if there is a finite matrix element of the Hamiltonian between states in which the electron is on site I and another situation where it is on site J, if this happens to be non-zero, then electrons can move from one side to another. So if this happens to be non-zero, then electrons can go from the neutral configuration to the ionic configuration. And in fact, this happens to be non-zero because the particular term in the Hamiltonian, the Coulomb interaction, for example. So let us write this as T. Okay, such terms. So basically, I mean, what you have to understand from here that there are terms in the Hamiltonian such that these matrix elements are non-zero. So therefore, so these configurations psi4 and psi5 are coupled, so they can mix. So then what we have to do? So when we consider ionic configurations, I have to enlarge my singlet space. There is not one singlet anymore. There are other singlets, and we have to look at that piece of the Hamiltonian. In fact, why not this configuration? So why not this one? Turns out that matrix elements between psi4 and psi6 will be zero because they have different parity. So that much is enough for us to understand. And we just carry the message from here that psi5 and psi4 can mix. So therefore, I have to enlarge this sort of Hilbert space. It's not 4-dimensional anymore. It's 5-dimensional. I have to include this, but then I forget about the triplet because singlet and triplet are not mixing. What is mixing is this singlet that I already had there and this singlet. So I have to look at that 2-dimensional space or subspace over there. And in that 2-dimensional subspace, the Hamiltonian is not diagonal because I have these off-diagonal terms, okay, between the neutral configuration and the ionic configuration. So basically what now I'm saying is, I have a 2x2 Hamiltonian in the singlet space, singlet subspace. So this was J12, the earlier one, psi4. But then here, what I have is an ionic configuration in which both the electrons are on the same orbital. So that obviously would cost some energy. So I have to include that energy term in this diagonal part. So that is, let's say, so what do I call it? I call it U1s, which is which is this integral. So if both of them happen to be on psi A, okay, 1 second. No, so the mod phi squared. Yeah. So I have to have So I have both the electrons on phi a orbital. So this is the sort of Coulomb interaction we have between them, and that is termed as U. So such integrals will encounter these again on several occasions. So such integrals, such Coulomb energies, when both electrons are occupying a certain atomic orbital, they go by the general name Hubbard energy, Hubbard interaction, Hubbard. These are basically on-site Coulomb interactions between two electrons when they are occupying the same atomic orbital. Okay, so I'll have a and so on. So I think this turns out to be 2t in terms of the t that I wrote. Okay, so now what is the task? This part of the Hamiltonian is not diagonal, so you have to diagonalize it. So to make matters simple, I even forget about J12. So all I want to see is that what is the effect of this t? So this is a simple exercise. You can ignore J. You just look at what is the effect of t on the eigenvalue of the singlet space. Okay, so that's a trivial task of diagonalizing a 2 by 2 matrix, and what you should be getting is the two eigenvalues, and then there was this and so basically then so I'm taking C12 equal to I12 equal to 0. So I'm ignoring these effects. I'm just focusing on what is the effect of including ionic interactions. So in that situation, this again, and the details I'll probably ask you to work out. So this, in this approximation is this is what we'll get. And if we take the limit, why is that important? We'll come to this. So this is large, or just say large. The lowest energy state turns out to be so what does that mean? When I neglect these things, the energy of the singlet state is simply this: two electrons occupying whether two different orbitals or the same orbital doesn't matter, because we have neglected these interactions. So the energy will be just twice the atomic energy. Okay, but then I have turned on these hoppings. So I have allowed ionic configuration. So if you have two different electrons in two different orbitals, from there, how can you get an ionic configuration? One electron has to jump from one atom to the other, hop from one atom to the other. So that is the effect of this term. T is the sort of strength of the hopping matrix element. So this actually lowers your energy. So that's the important point. That lowers your energy. In these conditions, what is the energy of the triplet state? It will simply be this, because you cannot have these hoppings in a triplet state, because two electrons cannot come on the same orbital if they have to make a triplet. Okay, they have to become a singlet. So triplet remains this. The singlet energy gets lowered. So therefore, if I calculate I'll get so this effect, that allowing electrons to hop from one atom to the other in the context of hydrogen molecule, it gives you ionic configuration, but we'll generalize these to lattice systems. This lowers your energy by this much. Lowers the energy of the singlet state by this much. So therefore, this favors an antiferromagnetic coupling. It's creating a singlet. So it's an antiferromagnetic coupling. And this exchange mechanism is called the kinetic exchange. So we learned about direct exchange, and now we learned about kinetic exchange. Direct exchange between non-orthogonal orbitals can be both ferromagnetic and antiferromagnetic, and kinetic exchange in the form that we learned here gives you an antiferromagnetic coupling. So what is the net exchange between two electrons? Of course, it's a more complicated thing where you have these. I mean, these are not zero. Then you have the effect of hopping and so on. But taking a simplistic approach, we say there is one effect which is direct exchange when I look at the effects of the C12 and I12 terms. Then there is another effect when I forget about these and I just look at the effect of this hopping term. I separate these two out. So then I'll write an effective J So the effective J12 is J direct plus J kinetic. And that, of course, is an oversimplification. But then, well, magnetism is a difficult topic. Questions at this point?
Sir?
Yes. Who is it?
Sir, I'm Manoj.
Manoj. Yes.
Sir, while calculating the energies of the hydrogen molecule, so from the beginning, we assume that the states can be factorized in spatial part and spin part. So, ideally, we should have started with the 4 different possible antisymmetric states and applied the variation of the 4 coefficients to reach the final answers. But why did we, a priori assume that the states can always be factored?
We did not assume states can be factored. It's just that states can be factored when you have a 2-electron system. As I told you earlier, when you have more than 2 electrons. So hydrogen molecule happens to be a 2-electron problem. So that's why states could be factored out. If you had a system which involved more than 2 electrons, you cannot factor them out. So that is one important point. So I'm not sure what exactly you mean by, that we started out by factoring the states. I don't know what happened to this.
No, sir, we have 2 different spatial wave function. One centered at nucleus A and another centered at nucleus B.
Right.
So they are different. And
right.
we have 2 spin wave functions, alpha and beta.
Right.
So out of these things, we can define 4 different antisymmetric wave functions. So we should ideally write our trial wave function as a linear combination of these 4.
Oh yeah, and you can do that exercise, but here solving the hydrogen molecule problem is not our goal here. And secondly,
Okay,
if you write a linear combination of those antisymmetric wave functions, you don't get a spin eigenfunction. So what I started out by saying is that because my Hamiltonian is spin independent, I should be able to have energy eigenstates that are also eigenstates of A square and AZ. So that's what we were interested in.
All right, yeah. Okay.
Yeah, any other questions?
No, sir.
Okay. Okay, so now what we'll do is, now that we have learned about kinetic exchange, we'll try to see what its consequences are for solids. Right. So let us step back a bit and go back to some of the basics we discussed in the early parts of this course. So what we said was that when we started learning band theory, when we looked at motion of electrons in this periodic potential, what we said, I mean, we of course came up with this band picture, and then we said that this band picture explains why some materials are, some crystalline solids are metallic and some are insulators. So let us now make it a little more concrete and define very precisely, well, more precisely, what are metals and what are insulators. And then we'll see why we are trying to go back to those questions. So, so we'll call a material insulating By the way, before I go further, let me ask you, so have you all been able to get a copy of this book by Fazekas? Is it available?
Yes, it is available.
Okay, good. So you can figure out which parts, of course, it's a huge volume, so I'm not discussing everything or all details. So you can figure out what I am doing. Also, I'm still working on those, but maybe after today's lecture or in a couple of days, I'll try to post some extracts from it, essentially based on that book, but with my sort of input in it. I'll share those notes with you.
Sir, could you please also tell us which part to read if possible? Like,
I'll try to do that. I'll try to do that. Sure.
Thank you, sir.
Okay, so coming back to this, insulators, so materials whose static electrical conductivity. Remember, this is one of the first things we attempted calculating in the Drude's theory. But anyway, it's the same quantity we are talking about. If the static electrical conductivity goes to 0 as temperature goes to 0, we call those materials insulators. And for metals, this is finite. Okay, there are other differences, of course, but let's not worry about that at the moment. I mean, the temperature difference of these two quantities are very different, but that doesn't bother us for now. And in fact, for superconductors, that is something we'll briefly look at after we finish our discussions. Magnetism, this can even diverge as T goes to 0. So, okay, so if we go back to band theory, so what is band theory? Band theory basically tells you what the effective one electron states are when electrons are moving in the periodic potential. So band theory, no matter how those bands are calculated, is essentially one electron or independent electron theory or picture. The band states are one electron states. Any band theory, no matter how the bands are calculated, as I said, we routinely do band structure calculations, but then at some point, some approximation is made, which basically gives us the total energy of the interacting system, but the states that are obtained are some effective one electrons wave function, the band states, the psi n k r's that we talked about. So band theory is essentially an independent electron theory. So in this, then, if we forget about magnetism for the moment, I mean, we have discussed these things, but I'm sort of emphasizing them once again because something very important will emerge at the end of it. So if at t equal to 0, if there are n electrons and t equal to 0, then n by 2 lowest energy me by energy we mean this quantity. So lowest energy band states will be occupied and the rest will be unoccupied. So this, an immediate consequence of this is that if you have to have, and we also have seen when we're discussing this semi-classical motion, that we have also seen that when we have partially filled bands, there can be conduction. When we have completely filled bands, the conductivity goes to 0. Those states do not contribute. So now in order to have this sort of completely filled bands, then the number of electrons to have, or just let me write this, completely filled bands would require that you have an even number of electrons per unit cell. Because if you have n states in a band, you have to have 2n electrons, and you have n states in a band when the number of real space unit cells is n. So in order to have 2n electrons, you have to have 2 electrons per unit cell. So the number of electrons per unit cell have to be even if you have to have completely filled bands and an insulating state. So insulators require that you have even number of electrons. I mean, according to band theory, that you have even number of electrons per unit cell. The reverse is not true. I mean, you can have metals with even number of electrons in the unit cell. And partially filled bands, or if you have odd number of electrons per cell, they have to give you partially filled bands and they have to be metallic. Another way of saying this is that the density of states. Earlier we called it G. That's a sort of, let me switch to this notation, but it's the electronic density of states. Rho at the Fermi energy is not 0 for metals. You have partially filled bands. And rho epsilon F. Now epsilon F, what is epsilon F for an insulator? It's halfway between the completely filled band and the completely empty band. So this is 0. So this is a condition for materials to be metals or insulators. So finite density of states at finite electronic density of states at the Fermi energy will give you metals. If it is 0, it will give you an insulator. There are exceptions to this. This picture holds. Let me introduce you to this idea. I'm not sure we'll have the chance to sort of discuss this in detail, but let's see. So this happens in strictly periodic potentials, something we have been studying so far theoretically. But suppose you introduce a lot of disorder in a solid so that effectively the potential is not periodic anymore. In those situations, so disordered solid, you can have rho epsilon F not 0, yet you can have an insulator. So these are called, this happens because this disorder localizes the electron states. The electron states are not extended over the entire system as it happens in this situation in metals in strictly periodic potential. The effect of disorder is to make the electron states localized. So the wave functions are localized in some areas to give you the very intuitive picture. And so therefore they cannot carry current. And this is called localization. And there is this, rich physics related to that. Okay, fine. So I'll leave it at that. So we're not getting into Anderson localization, but we are saying that in periodic potential, this is what you should have. Finite density of states at Fermi energy, metals, 0, you have insulators. What is the problem? Problem is, or before that, let me make one or two statements before I go to stating what the problem is. What is the time? Okay, we have a few minutes. Okay, so as I said, odd number of electrons per unit cell, sorry, even number of electrons per unit cell is required for a material to be insulating, but it doesn't guarantee that the material is insulating. And examples of that, I had mentioned this earlier, but maybe it will make more sense now than it did earlier, is that the alkaline earth elements like magnesium, calcium, strontium, even zinc, cadmium, etc. All these have even number of electrons in a unit cell, but they are all metals because of particular form of the band structure, which gives you partially filled bands. And just as you can have metals and insulators, I'll just want you to get familiar with these things, because there's a lot of research and discussion on various types of interesting materials currently. So you can have semi-metals, and you could have things like this. Sorry. So basically, I'm plotting schematically K and energy. Let's say I have a valence band. This is absolutely schematic. I'm not drawing it for any particular material. And they could just touch or just across each other. So this is the conduction band, and this is the valence band. They may just touch each other or just overlap by a tiny amount. So these are called semi-metals. And the interesting example of semi-metal is graphene. So graphene, in fact, you did this exercise. So if I plotted the band structure around this particular point in K space called the K point, this is capital K, this is just the index of the reciprocal space K. So you found that around the K point, the band dispersion is linear. So this is the conduction band, this is the valence band, and they just exactly touch each other because of the particular crystal structure and nature of the carbon valence states and so on. So all those things conspire. Now it turns out that there are other materials where you can have such situations, but nevertheless, in graphene, you have this kind of a situation where the bands are linear and they just touch each other. So this is a semi-metal. So these are examples of semi-metals. There are other interesting materials and band structures. We'll come to those later. I'll mention that when we get there. Okay. In fact, bismuth forms such a semi-metal. So where was I? Yeah. Okay. So then I'll take this statement that odd number of electrons per cell should necessarily give you a metallic system according to band theory, which is an independent electron theory. Now, what is our experience? And there the problem starts. Let me mention a few compounds, but most importantly, this. I'll talk about this because this is discussed in the book, so you can easily follow. So when you look at these, and there could be several others. When you look at these compounds, so let us look at this one. Now, in order to sort of argue this, you have to know what are the sort of electronic configuration of the atoms. So cobalt has 3d7, 4s2 electron configuration in the ground state. Oxygen, of course, is 2s2, 2p4. And then when I'm trying to figure out, so what am I trying to figure out? I'm trying to figure out what is the number of valence electrons per unit cell. So for that, I need to know what the unit cell is. The unit cell of cobalt oxide, it forms a rock salt structure. Now, this is where, when you try to understand actual materials, the crystal structure becomes important. You have to know what is a rock salt structure. It's a cubic structure, remember, we had discussed. If you have forgotten, you can look up your book. It's a cesium chloride structure, where basically you have one cesium and one chlorine atom per unit cell. So here you have one cobalt and one oxygen atom per unit cell. So then I can calculate the number of valence electrons in a unit cell. So it will be 9 plus 6, which is 15, which is an odd number. So according to band theory, this should be a metal. And that sort of completely throws our understanding out of the window, because cobalt oxide is an insulator with a band gap of something close to 3V, which is a pretty large gap. Okay, so what is happening? Something is going wrong. Now, experiments will tell you that cobalt oxide is an antiferromagnet. So some cobalt atoms have majority up spins, some other cobalt atoms have majority down spin. So therefore, if we consider the magnetic structure, I must have two cobalt atoms in the unit cell. So I have to enlarge my unit cell in order to be able to describe the antiferromagnetic system, right? I'm not looking only at the structural unit cell, but I'm looking at the magnetic unit cell. So I must have at least two cobalt atoms in the unit cell. Now, in order, if I have two atoms in the unit cell, you can argue that, well, then this count 15 is not correct, but it becomes 30. Now, the question is, if you do a band structure with that, do you get a metallic state? Or is your band structure method even able to describe that antiferromagnetic state correctly for cobalt oxide? Now, that's a discussion we cannot have in this course. That's far too sort of involves far too correlated electron physics. But the answer is, simple answer is no. Then there is another problem with that. What happens at high temperatures? High temperatures where it's no longer antiferromagnetic, antiferromagnetic order goes away. Then you are back to this 1 cobalt, 1 oxygen per unit cell structure. But then cobalt oxide then at that temperature should have become a metal, but it doesn't become a metal. It remains a robust insulator. Okay. So at high temperature, it's a paramagnetic. So at low temperatures, it's an antiferromagnetic insulator. And at high temperatures, it's a paramagnetic insulator. So that tells you that something is not right, or at least for this class of materials, our band theory is not giving the right picture. And in fact, it is not giving the right picture. There's more to it than what band theory tells you. So what is that? That is something we will take up next time. And in fact, that will connect this phenomenon as to why cobalt oxide becomes an insulator and an antiferromagnet. And these are not sort of independent phenomena. Le2CuO4 is another classic example of this. So these two phenomena are closely related. So that should go to further convince you that magnetism, A, is an effect of consequence of electron-electron correlations. B, magnetism is not an independent phenomenon. There are several other things happening in sort of these systems, which are all effects of electron correlation. So there's a hugely rich physics happening out there. And what we are trying to do is to get a small sort of peek into what magnetic consequences these have. And let me warn you that magnetism, as I said, one can give 1, 2 full courses on magnetism. So of course, we are not doing that. What we are trying to get is some sense of microscopic understanding of emergence of magnetic moments and magnetic order. There's a very rich phenomenology of magnetism, which we are not getting into, which we cannot get into. We cannot do everything in a few lectures. Okay, so I think I'll stop here today, and I'll wait for any